All right, welcome back to part two of Newton's first law of motion. And let's talk about our question we had at the end of the last one. First of all, if a car is going at the Texas Motor Speedway, can it keep a constant speed? And yes, it can. It could keep the same speed. Now, it can't be probably full speed or 250 miles an hour or whatever they usually do in a race on the curves, because they usually have to slow down a little bit on the curves. But if they took a slower speed, say 150 miles an hour, they could do that around the whole track, although it would have to adjust and so forth. They could have a constant speed, but could they have a constant velocity? And that question is no. Okay, perhaps on the straightaways where it's a little straight for just a little bit, but then eventually going to hit a curve. Once you start changing direction, you're no longer going in a straight line. You're changing direction, therefore you're changing your velocity, and you're not going in a constant velocity. So no, it's impossible to go around a whole lap at a constant velocity, but you could go at a constant speed. All right. So I just kind of touch on that. All right, let's talk about relative motion. No, this is not when your cousins come to visit, although that probably involves motion too. If I ask you right now, are you moving? Well, your hands or feet may be tapping, you may be bored, you may fall asleep and your head dropping down, so it's moving toward your desk. But in general, your whole body as a whole is not moving. It's just sitting here watching this video right now. So you're not moving. But in fact, right now you are on the Earth, and the Earth is hurtling around the sun at a speed of 100,000 kilometers per hour. Now that's kilometers per hour. If we change that to miles per hour, that's only about 45 to 50,000 miles per hour. Okay, but still pretty doggone fast compared to the sun, because you're spinning or revolving around the sun. At the same time, the Earth is also rotating, and we are rotating at a certain speed. Okay, so you are spinning along with the Earth. The whole Earth is going around the sun. So in fact, you, as being something on the Earth, are also moving at those speeds. So just for the record, you are capable of moving at 45 to 50,000 miles per hour. So the next time someone says you're slow, say, ha, what do you know? But since everything on Earth is moving at the same speed you are, you do not feel that. Okay, it's similar like if you're going in a car, it's going 60 miles an hour down the road, and someone's sitting next to you. All right. If you look across at them, it looks like they're just sitting there. They're not moving. Why? Because they're moving at the same speed as the car is. Anything in the car, if you toss something to them, it's going to just go from you to them, just like you were sitting on a park bench, because everything in the car, including whatever is in your hand that you toss to them, is moving at 60 miles per hour, and you're moving at the same speed. And so it appears like to each other you're not moving. All right. If you look at a car in front of you that's going 60 miles per hour, it may appear to be motionless sometimes. All right. You may have been at an intersection when you felt like you were running into the car in front of you, and actually it was because they were maybe they had a standard and they were slipping back toward you. All you could tell, it looked like y'all were moving together, and so you assumed it was you and slammed your foot on the brake pedal. Maybe you've not done that. I have. But as one of you is moving, it feels like, oh, I need to stop. Well, you're not actually moving. The other car is moving toward you. But it's all a matter of relative position. And so we talk about relative motion, or we talk about a reference point. Okay? When we say something is not moving, usually our reference point is what? Well, compared to the ground. Okay? And so, but if you're in the car and someone asks you if your passenger was moving, you'd say no, because compared to everything else in the car, they're not moving. Just like you're not moving, even though you're on Earth that's going 40 to 50,000 miles per hour. Okay, and so because compared to you and the Earth, they're all going that 45 to 50,000 miles per hour. In the car, everybody's going that same speed. But if you were to open that door and push your passenger out, which would not be very hospitable, but besides that, when you hit the ground, they would know that compared to the Earth, if that's the reference point, guess what? They are moving. Okay, and they're moving at 60 miles per hour compared to the Earth. And when they hit the Earth, it will be very, very painful. Okay, and so that's the idea of a reference point. Usually when we talk about a reference point of speed, we're comparing it to the ground or the Earth. And so if we say we're not moving, well, compared to the Earth, so that allows for all the movement of the Earth, because we're all moving on it at the same speed. All right. But say you're in a car and you flip a coin. Once the coin goes up in the air, is it still moving at the same speed? Well, when it was in your hand, was it going 60 miles an hour? Yes, it was. As soon as you flip it, it is still going 60 miles per hour forward. Once it's in the air, however, if you were to slam on the brakes so that the car slows down, the penny would continue to go at 60 miles per hour forward and would go forward perhaps into the windshield. Okay? If you were to slam your brakes while the penny is in the air, then the penny, if you were to speed up, then the penny would end up behind you, okay? Because now you're going faster than the penny is, all right? But any object in the air is going to be going at the same speed as the surface was when it left that surface. So, for example, if a bird sees a worm on the ground, when he's on the tree perch, it's part of the earth, and so he's moving at the same speed as the earth is. And when he jumps off the perch, he still continues to move at the same speed forward as the earth, and he ends up landing right where he saw the bug or worm on the ground and can catch it because they're moving at exactly the same speed. Just because the object leaves the surface into the air for a little bit, it still continues to move forward at the same speed that it was. Now, you've probably seen in Superman movies where Superman stops the earth from turning, okay, and then usually turns it backwards to run back time or something like this. Well, besides the time thing, the biggest issue would be if the Earth is rotating at however many thousand miles per hour, and you stop it, guess what's going to happen to everything not attached to the Earth? They're going to keep going at that same speed until they slam into something, okay? That would not be a pretty sight. If you were slowing from 45 to 50,000 miles per hour down to 0, it's going to take a while, and you're going to slam into something very, very hard. Okay, and of course that never happens in the movies, which is a good thing because then that would make Superman the mass murderer of the whole Earth, and that would look really bad on his resume. All right, the other thing about vectors, okay, is that vectors, like velocity, okay, besides being relative, depending on what your reference point is, they also can be added or subtracted. And since velocity, or speed with a direction, is a vector, then we can do that. So for example, in this we have a train car that's going to the right or left, depending on the train car, all right, at a certain speed. And then you have someone on top of the train car that's running either in the same direction or the opposite direction as the car at a different speed. Okay. Question is, what is the person's speed compared to the ground? All right. Well, to do that, it depends on whether the two vectors or forces are going in the same direction or if they're going in opposite directions. All right. So, for example, if you look at C, the man is running 4 meters per second to the right, and the car is going 6 meters per second to the right. So if they're going in the same direction, you would add them together, which means that this person would be going a total of 10 miles per hour to the right, would be its new velocity. All right. However, the other ones are all going in opposite directions. So if they're going in opposite directions, all right, so up here we have 8 meters to the right. The runner is going 4 meters per second to the left. We would subtract those, which would give us 4 meters per second. And it would be to the right or to the left. Well, the greater speed is to the right. So that means his net speed, if you will, would be 4 meters per second to the right. Okay, and this one down here we said was 10 meters per second to the right. All right, for B, we're going in opposite directions, 10 and 6. All right, so we would subtract them, which would also give us 4 meters per second. All right, but this time the bigger number, 10, is going to the left. So he would be going 4 meters per second to the left. So he would have the same speed as A, but he would have a different velocity because he's going in the opposite direction. All right. And for the last one, or D, we would subtract again. 18 minus 6 gives you 12 meters per second. All right. And his velocity would be to the right. Okay. And so all these people would have different velocities. Even though A and B have the same speed, they're in different directions, but they would have different velocities. So for velocities, usually we just assume in a picture that to the right is a positive number, to the left is negative, forward is positive, backwards is negative, but it really doesn't matter which direction is which, as long as you know positive is to the right or positive to the left. They could say either direction. So if we want to know which one has the greatest velocity, well, if we mean to the right, it would be 12 meters per second to the right. All right. And so keep in mind all of these velocities are relative or compared to the Earth, or to the ground. And so that has to do with the Earth being our point of reference. This brings us to Newton's first law of motion. All right, Newton's came up with 3 laws of motion, which basically kind of revolutionized a lot of the study of motion and so forth. He figured out some things that many people spent a lot of time trying to figure out, and he did it very concisely in 3 rules. It kind of summarized some of what Galileo said, and then he took it on to some steps ahead. Okay, Newton's first law of motion is this. Sometimes it's called the law of inertia because it involves inertia. Basically said objects at rest remain at rest, and objects that move will move at a constant velocity unless the object at rest or the object at constant velocity is acted on by a net force or an unbalanced force. Okay? In other words, if an object is just sitting there, it's going to just keep sitting there until some kind of force, unbalanced force or net force, acts on it. Otherwise, it's just going to sit there till kingdom come. All right? If an object is moving, it's going to continue moving the same way it is now, at a same speed, in the same direction, and it's going to continue to do that until an unbalanced force acts on it. Okay? Now, normally, up until this time, someone thought, well, if you roll a ball across the floor, and it goes boing, 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 eventually it's going to slow down. And people thought that, well, it slowed down because it ran out of force. Okay? But it's not that it ran out of force. It would keep moving. Inertia says that it would keep moving at the same speed unless some force acts on it. Now, the problem is people did not see a force acting on it. But if you go back to Galileo said, friction is a force. Okay? And so friction is the force that acts on a rolling ball and causes it eventually to stop. So it would keep going forever, but friction acts on it and slows it down. And that's the unbalanced force or the net force that acts on it to make it stop. You can't see friction really, and so we kind of think nothing's there. But there is a force, and very important, and it's almost everywhere. And so that's part of what kept other people probably from coming up with Newton's first law, is because he realized that friction was a force and things were slowing down only when a force acted on it, such as friction. All right. Now, in order for an object to move, then, if you have an object that's stopped, it has to overcome its inertia to get it going. And so it actually takes more force to get a stopped object going than it takes to keep it going. Okay? So, for example, if you have a car broken down on the side of the road, it may take 2 or 3 people to get the car moving. But once you get the car moving, assuming you're not going uphill, it may only take 1 person to keep it moving. Why? Because at first you have to overcome its inertia, and the more mass it has, the bigger it is, the more inertia there is to overcome. But once you get it going, all right, all you have to do is overcome the friction between the tires and the road and to keep it going. So it takes a lot less force to keep it going because there's not much resistance between a wheel and the ground. All right, and so it takes a lot of force to overcome that. All right. Now, a lot of what we see in movements, Newton said, had to do with 2 forces: gravity and friction. And gravity is actually the reason for friction, because gravity pulls objects down and makes them rub against each other and causes the friction. All right. And we measure that force, or all forces are measured in newtons, named in honor of Isaac Newton because he discovered the force of gravity. And we will stop there for our second part and continue on in a moment.